Hello, everyone. Welcome to my presentation. I am Shizhuang from Shanghai Jiao Tong University. It's a great pleasure to present our work on integrity monitoring of GNSS precise positioning with ambiguity fix. My co-authors are Professor Xingqun Zhan, Dr. Yawei Zhan, and Mr. Zhen Gao. Let's start from the background. We used to worry about integrity mostly in aviation. But now, more autonomous applications, such as autonomous cars and urban air mobility, are defining their requirements on integrity. So in addition to high accuracy, we need to provide high integrity for these applications as well. Speaking of GNSS-based precise positioning, we typically refer to RTK and PPP-RTK. Both can reach to a centimeter-level accuracy with a fast convergence, and both require correction products and ambiguity resolution. To provide high integrity monitoring is needed. However, there is few integrity solutions for GNSS precise positioning with ambiguity resolution. So, what we are going to do is to design an integrity monitoring algorithm for GNSS precise positioning against all sources of false and incorrect ambiguity fixes. Here is the outline. I will start with introducing the principles of GNSS precise positioning, using PPP-RTK as an example. Then is the key part, the integrity algorithm design. In our design, we develop a modified multiple hypothesis solution separation scheme, and it can handle the faults in the receiver measurements, the faults in the products, and the incorrect ambiguity fixes. And we provide a closed-form formula to evaluate the protection levels. Section 3. I will show some results. Let's begin with principles of GNSS precise positioning. For GNSS positioning, all we need are these two equations. In the pseudo-range equation, it includes the satellite orbit, the receiver position, the clock offsets of the receiver and the satellite, the receiver inter-system bias, the troposphere wet delay, the ionosphere delay, code bias, and white noises. For the carrier phase equation, the most important difference is that it includes a cycle ambiguity, and this is an integer. For PPP-RTK, the user will subscribe the correction products, including the precise orbit, clock, satellite signal biases, and atmosphere corrections. Accordingly, we need to estimate the user position, receiver clock offset, receiver signal bias, atmosphere delays, and ambiguities. To estimate this state vector, we need the state models, the measurement models, and the error models. They are given in our paper. In this work, an important assumption is that all the error terms are zero-mean white noises and they are uncorrelated with each other. With these models, we can estimate the state vector using a Kalman filter. It is a recursive estimator and equal to a batch least squares estimator. We also consider a sliding window least squares estimator. More details can be found in our paper. At this stage, the state estimate is called a float solution, because the ambiguities are not integers. The next step is ambiguity resolution. Now we have the float solution and its covariance. X has the structure like this. We are interested in positions and ambiguities. So, we define as X ambiguity, and B as X position. For ambiguity resolution, the first step is to fix the float ambiguities by integer bootstrapping. Integer bootstrapping fixes the ambiguities sequentially, as shown in these equations. These terms come from the LDL decomposition of PAA. The second step is to re-estimate the positions using the fixed ambiguities. This reduces the covariance of the position states, that is, benefit the navigation performance. Integer bootstrapping is only one choice for ambiguity resolution. We choose it because it offers a formula to evaluate the prior probability of the correct fix event and the incorrect fix events. After introducing the principles of PPP-RTK, we go to the next part, integrity monitoring. This figure is the flowchart of PPP-RTK. We can see, the threats for PPP-RTK include three parts, the faults in the receiver measurements, the faults in the correction products, and the incorrect fix events. Then we will show how we deal with these threats with integrity monitoring. First, let's have a look at the prior studies that support our research. Prior work on PPP, RTK, and PPP-RTK integrity monitoring can be divided into two classes. Some of them evaluated the protection levels for float solutions, for example, the work from Stanford University. Other studies considered ambiguity resolution and quantified the effect of incorrect fix events on the integrity risk. However, they assumed that the receiver measurements and the correction products are always fault-free. So our question is, what if measurement faults or product faults occur to an ambiguity fix-enabled GNSS positioning system? Can this gap be filled by a simple combination of prior approaches? The answer is no. See this figure: if the measurements or the products are faulted, the float solution will be biased, and the float ambiguities will also be biased. This will influence the ambiguity resolution process, that is, the risk from incorrect fix events will be different from the fault-free case. So, we design a new integrity monitoring algorithm to monitor measurement faults, product faults, and incorrect fix events simultaneously. Our approach is based on multiple hypothesis solution separation. Thank the authors of MHSS for developing such a powerful tool. Here are some definitions. Satellite fault is the event that the measurement or the product of this satellite is faulted. A fault mode is an event combination of satellite faults. In this figure, the first one assumes all the satellites are fault-free, and the second one assumes the first satellite is faulted. For each fault mode, we compute a subset solution, Xi, using the healthy satellites under Hi. Please note, the ambiguity states of the faulted satellites are not included in Xi. Based on MHSS, we can easily realize fault detection. The test statistic is the difference between the all-in-view solution and the subset solution Xi. The test threshold is determined based on the false alert budget, PFA, and the solution separation variance, which can be computed using this. If all the test statistics are within their thresholds, then there is no fault alarm. Otherwise, the algorithm will issue a fault alarm to the users. If there is no fault alarm, we can evaluate the protection levels or the integrity risk. The integrity risk for XQ is given by this equation. PL is the protection level. This is the integrity risk from one fault mode, and this is the integrity risk from the unmonitored fault modes. Let's focus on the integrity risk from fault mode I. In this equation, we consider the correct fix and incorrect fix events in the ambiguity resolution process. Delta I is the ambiguity offset for Xi. It represents the difference between the fixed ambiguity and its truth. We define delta I0 as the correct fix event, that is, delta I0 is 0. Others are incorrect fix event. Look at this blue part. This is a two-layer hypothesis. Hi is for the measurement faults and the product faults, and delta I is for incorrect fix events. So this shows how we deal with the faults and the incorrect ambiguity fixes. Let's determine the pink term first. Its upper bound is given by these two equations. The first one is for fault mode I, and the second one is for the fault mode 0. I delta I reflects the effect of the ambiguity offset on the integrity risk. Please check our paper if you are interested in the proof of these equations. Then we determine the blue term. This term is the probability of a correct fix event or an incorrect fix event. This probability can be computed by this equation. These terms come from the LDL decomposition of PAA. Specially, the probability of the correct fix event is given by this equation. It can be called the ambiguity resolution success rate. If you are interested in the proof, just have a look at the work of Professor Tunison and Professor Kanafsa. This is not the end. Look at here, we need to consider infinitely many incorrect fix events. Obviously, this is not okay. So, we need to determine the incorrect fix events that really need to be monitored. That is, we can only monitor a few incorrect fix events and make the probability from unmonitored events smaller than a preset threshold. In our paper, we provide a method to do this. However, we find that we still need to monitor many incorrect fix events if the success rate, PS, is small. So, to fix or not to fix, this is the question. In our solution, the ambiguities are fixed only if the success rate is higher than a preset threshold, for example, 99%. And especially, please note, if the all-in-view solution is not fixed, then all the subset solutions should be float. For the subsets that are not fixed, their contributions to the final integrity risk are also discussed in our paper. Finally, here is a flowchart of the integrity monitoring algorithm. First, we determine the fault modes that need to be monitored. For each subset, we obtain the float solution. According to the success rate, we determine whether to fix it. Next, we perform fault detection. If the fault detection test passes, we determine the incorrect fix events that need to be monitored. Finally, the protection levels are evaluated. Then we use simulations to validate the proposed algorithm. Simulation settings are shown in this table, including the constellations, prior probability of the satellite fault, integrity risk allocations, false alert budget, and some thresholds used in our algorithm. Let's check the results. Figure 1 compares the position errors between the float solution and the fixed solution. We can see, the fixed solution has a fast convergence and is more accurate than the float solution. Then, let us compare the protection levels. Figure 2 shows that the fixed solution has lower protection levels. So, this slide proves that ambiguity resolution can benefit both navigation accuracy and integrity. Figure 3 shows the protection levels and the position errors in one figure, in a fault-free condition. We can see, the protection levels always safely bound the position errors. Figure 4 shows the test statistics and the thresholds in a fault-free condition, using subset 1 as an example. As shown in this figure, there is no false alert event. Then, the fault detection capability is tested. We simulate a case, where there is an undetected cycle slip of 2 cycles in satellite 1. Figure 5 shows the protection levels and the position errors, and Figure 6 shows the test statistics and the thresholds for subset 1. In Figure 6, the red point indicates the epoch when the fault is detected. And we can see, the fault detector can effectively detect the fault. And as shown in Figure 5, before there is a fault alert, the protection levels always safely bound the position errors. These results prove the effectiveness of our algorithm. The results before are based on Kalman filters. And in this slide, we also show the results with a sliding window least squares estimator. The length of the window is 30 seconds. Figure 7 shows the position errors and protection levels, for both the fixed solution and the float solution. We can see, the fixed solution, that is, the blue point and the black dashed line, has better accuracy and lower protection levels than the float solution. An interesting finding is that there are 2 jumps in the protection levels in this figure, here and here. This is actually caused by that the all-in-view solutions are not fixed at these epochs. Why are they not fixed? To answer this question, we present the success rate of the all-in-view solution and the subset solutions in Figure 8. Now the reason is clear. The success rate is low at these epochs, so the all-in-view solutions are float. In future work, we will consider partial ambiguity resolution to overcome this issue. In conclusion, we develop an integrity monitoring algorithm for GNSS positioning with ambiguity resolution, based on multiple hypothesis solution separation. We derive the formulas to evaluate the protection levels. Our algorithm can monitor measurement faults, product faults, and incorrect ambiguity resolution simultaneously. Simulation results suggest the effectiveness of this algorithm and show that ambiguity resolution can benefit navigation accuracy and integrity. In our future work, we will focus on designing the fault exclusion function, supporting more ambiguity resolution methods, and considering time correlation. Thank you for your attention. I have uploaded the full text to my website, and you can have access to it by scanning this QR code. If you have any questions or suggestions, please feel free to drop me an email.